Slopes, Part 2. Here are your priming questions. As a quick review, from Slopes Part 1, that was going to be on video 106, we talked about DT, VT, and AT graphs, and how we can go from a DT to a VT to an AT, which this video will go more in depth into. And as a quick reminder, when we are looking at slopes, there are two categories of characteristics that we want to examine. The first is whether it's positive or negative, or zero. And the second set of characteristics is whether it is increasing, decreasing, or constant. And remember that these sets of characteristics are independent of each other, and each will tell you something unique about the motion of the object. And remember that this is where we introduce acceleration as the change in velocity over time. These key points still apply. And as a quick reminder, with a single graph, and in this case we had a parabola, we can have a curve that has a slope that is both increasing, which is it is increasing over here, decreasing on this side. We have a curve that has a slope that is positive on the left side and that is negative on the right side. And so we can have a single curve with multiple characteristics. And so you need to be careful about breaking down the slope into parts for those types of graphs. Now I want to spend a little bit more time with VT graphs and what that tells you about the motion of the object. In this first example, we see that we have a horizontal line. So the slope value is 0, and so whatever value the velocity is, that means that the velocity is constant. It is going at the same velocity, which also means that if it is positive, like this one shows you, then we are constantly increasing in our displacement because we have a positive velocity that is constant. So that would be as if you're traveling north at 20 miles per hour forever, or for however long you're measuring the time, you're going constantly at 20 miles per hour, so your displacement is continuing to increase. Now this middle one, we can see that our slope is positive, so our velocity is increasing, and it is a constant slope, so it's increasing at a constant rate. It's as if you held your foot on the gas pedal and it increased in velocity at the exact same rate through the entire time that you had your foot on the gas pedal. This next one is a little bit more complicated. We can see that the slope is negative and it's constant, but what's interesting here is the velocity begins positive, then it crosses the x-axis, and then it becomes negative. What this means is we have a large positive velocity to begin with. It decreases at a constant rate. At some point, the velocity becomes 0, so for a moment, it is still. Once it passes that moment, then it becomes a small negative to a larger negative velocity. The easiest example for this is tossing a ball up and following the change in velocity over time. When you first release the ball, you're going to have the highest positive value, if up is our positive direction. At some point at the top of its trajectory, it's going to change directions, and at that moment, it has 0 velocity, and then it will gradually accelerate down. And so that's what it's going to be, a negative velocity here. And now we get to AT graphs. You have 3 AT graphs here on the screen. We're going to go through each one of them, and each tells you a unique story about the motion of the object. The first graph here we can see has a positive value and a 0 slope. It is a horizontal line. In this case, what this tells you is that our acceleration is positive and constant, which means that we have a constant change in our velocity, and that change itself is positive. We go to the second graph, and we see a different story for a different object. We start with a positive acceleration. At some point, the acceleration becomes 0, where it crosses the x-axis, and then the acceleration becomes negative. And so we can see that the acceleration changes over time, and this will change the velocity over time. And based off of those values, if we had the actual numbers, we could figure out what the change in velocity actually was. For this last graph, we have a horizontal line, and it is at 0. It is on the x-axis. So in this case, we can say that our acceleration is 0 meters per second squared. But what we have to be careful about with this particular graph is that this is not necessarily saying that the object is at rest. It could be, but all this is really saying is if our acceleration is 0, that our velocity is constant. Whether or not that velocity value is 0 depends on the problem. It could be, but it also could be a constant non-zero velocity. It could be positive or could be negative. It depends on the problem. So that's what the 0 meters per second squared means for us. Now, what I want us to do is I want us to be able to look at a dt graph and be able to construct a vt graph, and then from the vt graph, construct an at graph based off of the slopes. So if we were to look at this, what we see here is that our dt graph shows a positive displacement to begin with, and it becomes a smaller positive at the end. If we look at the slope here, we have a constant negative slope. So constant negative, we would graph that like this. And actually, let me use a different color. So this would look like this. So we have a constant negative slope, right? We look here, we see that it is negative, and we can see that it's a line, so it's constant. So negative and constant. And now to the AT graph, we look at the slope of our VT graph, and we see that our slope itself is 0 and constant. So that means that we would draw our AT graph like this on the x-axis. And if you look at this, we can see that we have an acceleration of 0 meters per second squared. We have a negative constant velocity, and our displacement is changing from the positive and decreasing. So again, this goes back to the idea that 0 meters per second squared for acceleration doesn't necessarily mean that our object is standing still. Let's look at the next one. And this one will take a little bit longer. In this case, I want to again show you the change in the slopes. And so here, I again am going to split this problem in half. And just as before, we can see that our slopes initially are a positive slope with a very high magnitude because they're so steep. And over time, until we get to the end of the first half, the slopes remain positive but decrease in magnitude. Ultimately, at the very top, and this needs to be tangential, at the very top, the slope is 0. And then from there, if we were to, actually, let's go ahead and draw this out on our VT graph. So again, we're plotting the slope values, and these are all qualitative. So we start out high and positive, and we get to a 0 value at the very peak over here. And now, if we start plotting these out, we get to a small negative value, and ultimately to a high negative value. And so, the way that your VT graph would look would something like this. So we start out with a high positive, that's this initial slope value. We get to a point that is a 0 slope value, that's where it crosses the x-axis, and then it becomes gradually more negative, so increasing in magnitude, but negative. So it would look like that. Now from here, we can see that this is or at least it should be, a straight line with a negative slope. So it's a constant negative slope, and that would look like this for our AT graph. So our AT graph with a negative acceleration is from a displacement graph that has a parabolic curve to it. And the last one, this one is going to be the most complicated. In this case, we can see that our slope is constantly changing, and we can see that initially it has a high positive value. As we draw more slopes, though, we can see that it becomes more and more gradual over time. But these are all positive slopes. And so we start with a high positive, and then we become a low positive, but it is gradual. And so when we draw this out, this will actually look something like this. It will also have a curve. Oop. And don't mind that blip. Let me go and erase that. When we look at this graph now, we need to look at the slopes on this line, and we can see that initially we have a large magnitude negative value, and that over time the slope itself becomes less and less negative, but always stays negative. And so if we were to draw out the slope on it for an AT graph, we would start with a large negative value, and then it becomes a smaller negative value, something along the lines of this. And so we have our dt, our vt, and our AT graphs. And remember, these are all related through the slopes. The slope of a dt graph, the instantaneous slope, will give you the plots for the vt graph, and the instantaneous slopes along the curve for a vt graph will give you your AT values that you can plot and produce that particular graph. And here are your priming questions again.